In this video we're going to look at mass spectroscopy. Okay, so the diagram there shows kind of a simplified version, I suppose, of what we would see in a mass spectrometer. And the reason that we have these mass spectrometers, or what they're used for, would be for identifying the different isotopes of elements and also finding their abundances. So mass spectrometry would be used for drug testing, it would be used for environmental science, for finding the any isotopes of any elements present, let's say in water samples, we'll say, and also it would be similar also to gas chromatography that we'll come across later in your course. So we'll talk about the principle of mass spectroscopy first, and that is that charged particles, we now know that they would be called ions, moving in a magnetic field are deflected to different extents according to their masses and are thus separated to these masses. So that's the principle of mass spectroscopy that you must learn of. Inside in the mass spectrometer then, there are 5 processes that take place. They're vaporization, ionization, acceleration, separation in a magnetic field, and detection. Okay, so in vaporization, right, a small amount of gas or liquid is injected. Okay, so a small amount of gas or liquid is injected. Now, once you enter the mass spectrometer, that whole environment in there is actually a vacuum. Alright, so the environment in there is a vacuum, and that means that any liquid, alright, that enters that vacuum actually turns to a gas. Okay, so vaporization, vapor, turns to a gas. Okay, so the gas obviously stays as a gas. Any liquid that is injected there goes to a gas. Alright, we'll also see later in another stage why it is important that there is a vacuum in there. Alright, so you inject anyway your small amount of gas or liquid in there. And next you come to ionization. So ions, we should know anyway already, are charged particles. Right. So in this ionization, right, you're creating positively charged particles. Okay. Here you have an electron gun, and what this electron gun is, it essentially fires electrons at the atoms or molecules that are passing by it, and they knock out other electrons out of it, so removing electrons essentially from the atom. If you remove an electron, you have extra positive charges left in your atom or your molecule, so it becomes positively charged. Okay, so kind of a representation of that would be, so X is just kind of we're using it to represent an element. Okay. And that's your positively charged atom then. It's 2 electrons. Okay, we also say that it's in its gas state. Okay, there at the G. Okay, so once it becomes positively charged, we see here we have negatively charged plates, right? And this is where the acceleration process happens. The positively charged ions are attracted to that negatively charged plate. So if they're attracted to it, they speed up. Right, they speed up. Of course, some of them just hit off the plate, alright, but there's a small gap, alright, in the center of the plates that allows a small beam of those ions to pass through. Alright, they're going with quite a momentum at this point that they pass through. Okay, but one small beam is allowed through. And that's your acceleration stage. Again, it's important that this takes place in a vacuum, because if it didn't take place in a vacuum, there would be air particles present that your ions would be deflected by. Okay, they'd change their course. Okay, so it's important that this takes place in a vacuum, so your ions don't collide with any air particles. Next we move on to the separation in a magnetic field. And in here, all right, it kind of does what it says in the tin, really. All right. So your ions are separated, all right, based on their masses. So these, this reddish brown area, that's what they're representing as a powerful electromagnet. So lighter particles are deflected much easier. So your light particles, when they reach the electromagnet, will be deflected quite easily, and they will maybe collide with the side of the mass spectrometer there. All right. Some of your ions, one particular isotope of that element, will reach the detector, and we'll come on in a second to the mass spectrum. And the heavier particles are much more difficult to deflect, so they won't be deflected as much, and they will also collide with the other side of the mass spectrometer. Okay, so at that point you're only detecting one isotope of it, so we would decrease maybe the magnetic field, we would decrease the strength of the electromagnet, and at that point then the lighter particles would reach the detector. If we increase the strength of the electromagnet, well then the heavier particles are being deflected, and they will reach the detector. Okay, so they're separated based on their masses. I suppose that's the goal of mass spectrometry. Alright, and then we come to the detection stage. So this detector is very, very sensitive, and picks up on any isotopes that will reach it. And from there, a mass spectrum is created. And the mass spectrum are quite simple, really. Alright. Let's see. Alright, so we have, sorry now, these lines aren't very straight, but we'll get the picture. Alright, so on these mass spectrum, on the bottom you'd have the mass, okay, or the relative mass detected, and then on the side here you'd have the abundance. Okay. So you'd have the abundance. So let's just, for sake of argument, one we're familiar with, we were talking about chlorine. Alright, and we said that 75% of chlorine was found as chlorine 35. Okay. So on our mass spectrum, that would come up as this, just in a straight line. Okay, and that 25% of it is in, has a mass of 37. So that would be our mass spectrum for chlorine. Okay, so you have your abundance and your mass then also. Okay, and that's your 5 stages of mass spectrometry. Or mass spectroscopy, sorry.